right. How was your break? Was good? Somebody cranked the mic up a little bit too much. So I actually went to a union picnic on Monday. So my wife said, this is the first time, or in a very long time, that we actually did something that relates to Labor Day on Labor Day. All right. It's almost time. All right. So what I can do, I think the recorder is on already. Let me just double check. Yep, it's already on. So what I'll do is I'm going to go back to the recording of the previous class, just as a, previously, you know, like, at the beginning of each episode in a series, they always have, they play the theme music and then replay certain scenes, previously, something happened, right? So we'll do about the same thing without all the dramatic effect. So the last time we met is 1 week ago on the 29th. And let's see, maximize that. Okay. So I believe what we did at the end of the previous class was to use a function and C code to explain the concept of universal versus existential quantifiers. So is that helping you kind of to remind you, what we did last time? Because we talked about for all, which is the inverted A symbol. We also talked about the kind of flipped E symbol for exist. So if we say for all x such that P of x, okay, P being a predicate, or you can see it as a Boolean function, or a function that returns a Boolean value, then the function u, okay, is basically doing that logic. The function u is having a local variable result initialized to true, and then for every single possible x in the entire universe, because I did not quantify what x I should be considering, then we'll consider everything that is and that exists. And what it would do is to evaluate p of x. It returns a Boolean value, a true or a false, and then that result is ended, or using a conjunction, to join with result. So that means if there's nothing in the entire universe, then the result of the entire function is by default true. Okay? On the other hand, if there's one thing in the entire universe that makes p of x false, then the result is going to be false. So is that okay? That's basically what we call the universal quantifier, which says, for all x such that blah, 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 blah. Is that helping your understanding with that, for all concept? So there exist is kind of like the flip side of it. So let me see if I can play this video there you go. Okay. So with there exist, it is almost exactly the opposite, but not quite, because you cannot have one but not the other. There exists x such that p of x is going through something like this. The structure looks almost the same. Yes. Yes, I am recording. That's all right. So with there exists, the local variable result is initialized to false, which means if there's nothing in the entire universe, then the existential statement is by default false. Okay, cannot possibly be true. But on the other hand, if there is at least one thing in the entire universe that makes p of x true, then result is going to be true. Now, because result is ORed with p of x, so that means once result is true, it cannot become false again. It only takes one thing of the entire universe to make p of x true, then it is going to return a result of true. So that's kind of where we stopped a week ago. And what we will do today is we're going to go back to the set theory, but using quantifiers to explain those concepts, which I accidentally, I flipped the order. So I used that one, I introduced those concepts before introducing the quantifiers. So that's why, and we're going back to that concept. And then, your homework assignment is set theory. It is your homework assignment, even though it looks like a quiz, it's not a quiz in a traditional sense, because you have an entire week to do it. Once you start, you don't have to finish it in half an hour or an hour. You have until like next week to finish it. So we're gonna go back to this one, just kind of quickly because we talked about this one already. I'm just going back to it, so it's just so that we can revisit the definition of some of the symbols in set theory or set notation, but this time we're going to use quantifiers. When we have two sets, okay, x being a set and y being a set, then they equal each other if and only if, okay, let's use the shorter form first. So the short form basically says, set x and set y are considered equal if you consider everything in the entire universe, okay? If one thing E is in x, it has to be in y. If it is in y, it has to be in x. If it's absent in x, it has to be absent in y. If it's absent in y, it has to be absent in x. So that's the power of this symbol, equivalence, or if and only if. Is that okay? All right. So that's equality between two sets, and then we have a description of what thing is inside a particular set. So this notation here, E equals to brace, open brace, x such that P of x close curly brace. That's basically saying the same thing as this, okay? Consider everything in the entire universe for all x. And then it says, if something is in E, it has to meet the requirement of P of x. P of x has to return true. If something is not in x, P of x has to be false. Turn around. If P of x is true, it has to be in a E. If P of x is false, then x cannot be in E. So once again, it is the power of the equivalence operator, or if and only if, that basically says, if one side is true, the other side has to be true. If one side is false, the other side has to be false. And it goes in both directions. It's bidirectional. All right. So is that okay? How we describe, the content of a set using a predicate. You can kind of look at P as a filter, okay? What is in and what is not in a set, okay? It's just a filter for that purpose. We can talk about the empty set, okay? The empty set, in this case is, S is an empty set. It is not the case that there exists at least one element x in the entire universe such that x is in S. Okay, that's basically saying S has nothing in it. S is empty. We can talk about intersections and unions. So right here we have intersection first. So if you consider everything in the entire universe, if x is in the intersection of A and B, then x is in A and x is in B. If x is not in A intersecting with B, then x in A and x in B has to be false. Now, it doesn't mean that x cannot be in A. It just means that x in A and x in B has to be false. So it can be in one of them or none of them, but it cannot be in both of them. Okay? And then the other way around is true too. So every time you see this symbol, if and only if, make sure you read it the other way as well. Okay? So in this case, we can also say, if I can find something that's common to A and B, then that something is going to be in the intersection of A and B. On the other hand, I find something that is not common to A and B, then that something cannot be in A intersecting with B. Is that okay? Union is kind of the same thing, except we flip the symbols upside down. The and becomes the or, the intersection becomes a union. Otherwise, we are talking about pretty much the same thing. And then we talk about the Cartesian product and also the concept of a subset. But eventually, ultimately, we're talking about basically the same thing. A is a subset of B if and only if you consider everything in A, it has to be in B. Okay, for all elements that are in A already. So that basically bind E to something that is in A. Then this statement has to be true. E has to be in B as well. There's an implicit implication here. The implicit implication is we're considering everything in the entire universe. If it is in A, then it has to be in B. So the arrow goes from left to right. It is an implication. Are we doing okay so far with all of these concepts? Yes? Then B is a subset of A. Then because you're flipping the symbols, right? So ignoring this side, if you're flipping the A and the B here, then you just flip it on the other side. So the B is a subset of A.
Is that an equality can be like subset of this?
Yes, you can use subset to define equality. Um, A is a subset of B and B is a subset of A implies that A equals to B. Well, I should say if and only if A equals to B. All right. And then we have proper subset. Proper subset is kind of the same thing as a subset of, except that you have one attached condition, you throw an and, where you have to be able to find something in B that is not in A. Okay? So that's why this time it's an existential quantifier. We just have to find one single thing that is in B, but it is not in A. So this not applies to the entire expression of x is in A. There's a hidden parentheses around x in A. All right. So are we okay so far with the set notations and the concepts? It's good? All right. So if this is okay, then we're going to move on. And you can do your homework. We are meeting on Monday, so if you're working on your homework assignment and you have some questions, feel free to bring those questions to class, okay? So what we'll do now is we're moving on to the discussion of functions. And since you're in this class, you must have met the math prerequisite, which is math 370. I think that's pre-calculus. And pre-calculus has a prerequisite of, I think, algebra. Am I correct about that? Okay. So that means you guys are you have to have some exposure to mathematical functions. So in mathematical function like log or exponent of sine, cosine, absolute value, and stuff like that, that's continuous. Okay, so you have been exposed to the continuous version of functions. In this class, because of the name, we only consider discrete functions. Okay, where we work with discrete values. Okay, so we'll take a look at the notations and then we'll take a look at the concepts first. So first we talk about tuples. We have seen tuples already. So a tuple has this syntax in this class. It's surrounded by round parentheses, and then items in it are separated by commas. So it looks like a set notation, but there's a major difference. In set notation, we use curly braces, not parentheses. So that's one. The second one is in a set, you cannot have duplicate elements. In other words, you do not list 1, 2, and then 1 again in a set notation because you cannot have two duplicate elements in a set. Also, in a set, the order of elements, how you list the elements, is not important. It's insignificant. So if I have a set that has 1 and 2 as elements, it doesn't really matter whether I write it as 1, 2 or 2, 1. They are identical, okay? In a tuple, on the other hand, ordering is important. So the tuple, the 3 tuple, 1, 1, 2, is different from the 3 tuple, 1, 2, 1. I said 3 tuple to emphasize that the tuple has 3 things inside. So sometimes you can just kind of ignore that and just say the tuple. Other times you can emphasize that there are 3 items as a 3 tuple or 2 items as a 2 tuple. Okay? Are we okay so far with the concept of what a tuple is? All right. So regarding tuple, there are some additional syntax that I use. If you want to designate a particular item inside the tuple, so let's say T, uppercase T is a tuple, and you want to address, or when you just want to say, okay, I just want that element at position I, so I borrow this from array notation. So T in square bracket I is designating element I inside the tuple T. Because for the most part, you can look at the tuple as if it is an array. Ordering is important. You can have duplicate values. Hey, arrays does all that too. Okay. And the last one is I also borrow the cardinality symbol from that applies to sets. We also apply that to tuples. So that returns the length of a tuple. If your tuple has nothing in it, it returns 0. If your tuple has 1 item in it, then it returns 1. Okay. So with this additional terminology, now we can start to get into the discussion of functions. So we'll go ahead and define, functions that you are quite familiar with. Okay, something like that. F of x equals to 2x. So the idea is, if you apply the function to a constant of 2, it will give you a value of 4. If you apply the function to the value of 0, it will give you a value of 0. If you apply the function to 0.5, it will return a value of 1. So that's not different from how this is how you have known functions up to this point. But in this class, we look at a function as a map, and not only that, we look at a function as a set of tuples. Okay, so that may deviate a little bit from what you understand functions as in all of your other classes. So we have terminologies. So when we say something like this, okay, so when you look at this notation here, it basically means f is a function, x is the domain, and y is the codomain. So let me say that one more time. This means f, lowercase f, is a function. It maps elements in x, which we call the domain, to elements in y, which we call the codomain. The concept of a codomain has a few other names. Some people call that range, okay? But in this class, we just call that the codomain. So domain is where you start, codomain is where you end. And the mapping is going from the domain to the codomain. So are we okay so far with these terms? A function is a set of tuples. Its job is to map elements in the domain to the codomain, okay? And this is the notation to basically say that f is a function that maps x elements in x to elements in y. Okay. So what we're going to do now is to use the function that we looked at a little bit earlier, which is f of x equals to 2x. But this time, we have to be very careful because we have to specify what we consider as our domain and what we consider as our codomain. Because we can choose the domain incorrectly and then something not unexpected can happen. So in this case, we are looking at a function f, which is the same function that we have seen before, f of x equals to 2x, but we'll see it as a function that maps integers to integers. This funky looking z is representing the set of all integers, positive, negative, and 0 itself. Okay. But remember, I said a little bit earlier, we look at functions as a set of two tuples. So in this case, in this very specific case where f of x equals to 2x, and I choose integers as is domain and integers also as is codomain, then I can kind of enumerate the elements like this. So the first element here, 0, 0 as a two tuple, is basically saying we are mapping 0 to 0. Okay? The second one is saying we are mapping 1 to 2, we are mapping 2 to 4, 3 to 6. Now obviously there should be something in the on the negative side. We are mapping -1 to -2, -2 to -4, and so on. But obviously this is not a very good way to describe what elements are in a set. So the best way to do it is to borrow something that we have talked about in the past, or just in the past 15 minutes or so, is to use this notation here. F is a set, okay? It's a set because we can see the curly braces. What does it consist of? It consists of two tuples. And the two tuples have a particular pattern. The first item of the two tuple, if you double it, it becomes the second item in the two tuple. So that's the pattern. But what can be x? X has to be an integer. Is that okay? So this describes, the function that maps integers to 2 times whatever that integer is. Are we doing okay so far? Yep.
You could also say that function maps real values to real values, even if we only put in and get out integers. Why would we constrict it to just
Integers. Because real numbers are not, the set of real numbers is not quote unquote discrete anymore. We call the set of integers discrete because of a concept that we haven't talked about yet. The set of integers is called countable, but the set of real numbers is not countable. So in this class, we are confining our discussion only to sets that are countable. So we are not considering real numbers. But integers is fine, natural numbers are fine, rational numbers are fine, but not real numbers. All right. So the bottom notation here is really saying exactly the same thing, except it's just a lot more verbose. Okay, it's basically saying, let's pick x as an integer. Then we pick y as an integer. As long as x is an integer, y is an integer, then we look at this if and only if. So the if and only if is basically saying, if we just so happen to choose a y that is 2 times x, then xy as a two tuple has to be an element of f. Okay? If we are not so lucky and we chose a y such that it is not 2 times x, whatever we pick x and y, if that is false, if x equals to 2x is false, then xy cannot be an element of f. Flip it to the other side, it's true as well. You look at bag, you look at f as a bag, right? You pick an element out of it, okay? You say, oh, okay, I get this element here, x is the first item, y is the second item in the tuple. If that is true, if xy is in f, that means y equals to 2x also has to be true, okay? On the other hand, you pick something, okay, out of the outside of the set f, in other words, xy is not in f, then this has to be false. Is that okay? So that's the power of if and only if. Okay, you can go in either direction. False implies false, true implies true, and then flip it in the opposite direction and the same thing. All right. So are we good so far with all of this stuff here so far? Okay. So this is a really vague description of what a function is or what qualifies as a function. So now we go in and we describe what a function really is in a little bit more technical terms. The first thing we notice is if you take the domain X and then you take the domain codomain Y and you make a Cartesian product out of it, the function that maps from X to Y has to be a subset of this Cartesian product. Is that making any sense to you? If you think about it, a function maps from the domain to the codomain. Okay? If you pick a two tuple out of a function, consider it as a set, you pick an element out of it, it's a two tuple. The first item of the two tuple comes from the domain. The second item of the two tuple comes from the codomain. And the meaning is, oh, this thing that I find in the domain maps to this thing here in the codomain. That's what a two tuple is saying. Okay? So a function as a set is basically a set of two tuples where the first item comes from the domain and the second item comes from the codomain. Yes?
Why wouldn't f just be equal to x?
It cannot be equal to because of some other restrictions. So we'll get to that. Okay, that's a very good question, but it is not equal to, but yet it is not less than or equal to. It's not a proper subset of either. Yep.
That was my question.
Okay, so it's not a proper subset of either, not all the time, okay? There's only one case when it can be, okay, two cases where it can be a proper, no, only one, there are two cases where it can be equal to, and then for all of the other cases, it's actually a subset, a proper subset of. Okay, so we'll talk about those special cases. Okay, but for now, I think it sort of makes sense that we are, whatever is in F is also going to be in the Cartesian product between the domain and the codomain. Is that okay? Because when you look at the Cartesian product of the domain and the codomain, it's basically just giving you every single possible pairing where one item is coming from the domain, one item is coming from the codomain. Okay? But the function is a lot more specific than that. Okay? All right. So this is the first thing that we notice. Let's see what else we notice. In addition to this observation, there's another important criterion for a subset X of X cross Y to be a function. So we'll highlight it, the English version of that statement. Each element of the domain must be mapped to one and only one element in the codomain. Okay, what does that mean? Yep.
We have one answer, so if there's a 3 for your x, you can't have an equal 6, 8, 7. Or map a 2, you can't have 6, 6, and 6, 7.
Correct. So one thing in the domain cannot map to two different things in the codomain. Yep. Right. But you cannot be missing either. So you cannot have one element in the domain that that's not mapped to anything. So that's why it's one and only one. Because if I only say one, there's an implication of at least one. So I have to say one and only one to basically say that, nope, it's exactly one. It's neither at least one or at the most one, it is exactly one. Is that okay? All right? All right, so now is a good time for some examples, kind of to help you consolidate all of these concepts. So let's go ahead and do a few examples. I can use a text editor to do some of this work so I don't have to resort to my tablet. Okay, so let's go ahead and just randomly pick some domain. Okay, so let's say the domain only has A, B, and C as elements, and then the codomain only has 1 and 2 as elements. Okay, so now I want to consider a function f. Okay, so function f is mapping the domain X to the codomain Y. So the dash greater than is my approximation of an arrow pointing to the right. Okay. All right. But this doesn't tell me exactly what the mapping is. So I'm going to list the mapping, and you tell me whether it is okay or not. So is that a function? F is an empty set, but we know that the domain of f is x, which is ABC, and the codomain of f is y, which is 1, 2. Can this function be an empty set? It cannot be an empty set. Which rule are we, upsetting or violating by making f an empty set? Well, right now it's not mapped, right? If f is an empty set, then A maps to nothing, B maps to nothing, and C maps to nothing. They have to map to one and only one thing in the codomain. Okay, well, f being an empty set is not possible. Okay, we'll just say it does not work. What about this? We'll say A maps to 1, and then B maps to 2, and that's it. Would that work? Is f as a set a function? Does it meet the requirement of every element in the domain has to map to one and only one element in the codomain? No, it doesn't work because C doesn't map to anything. Okay? Yep.
Can I ask one thing about that? So each element must map to one and only one element.
To be more specific, may I just kind of add to it?
Yep.
It's every element in the domain must map to one and only one element in the codomain.
And so,
Yep.
but multiple elements in the domain can point to the same element in the
It doesn't say it cannot, right? So, very good observation. Very, very good observation. So this B2, C1, okay, does work, okay, that's fine. Because, even though both element A and element C from the domain map to exactly the same thing in the codomain, it's okay. Because we are only counting. They don't have to be unique. We are only saying that every element, A, B, and C, from the domain has to map to one and only one element in the codomain. I didn't say unique. So that means if I want to, they can all map to 1 if I want to. But what about 2? 2 is not mapped to. It's fine. The restriction of mapping to only applies to elements in the domain. It doesn't say that every element in the codomain must be mapped to. Okay? So let me illustrate what I just said using a concrete example. B1 and C1. That works too. It meets the requirement. Every element in the domain, A, B, and C, maps to one and only one element in the codomain. But they all map to the same thing. That's fine. What about 2 in the codomain? It's not mapped to. The requirement doesn't specify that. Are we doing okay so far? Okay. All right. So I'll give you an example where it does not work. Okay. So A1, A2, and then B1, and then C1. That does not work. Okay. It doesn't work because now we have one element in the domain A that is mapped to 2 things in the codomain. Well, that doesn't sound like one and only one anymore. Does anyone want to argue that 2 is still one and only one? No. So that doesn't work. So let me specify and emphasize that this doesn't work. Okay. So now you have a few examples to basically say, oh, okay, so there are many ways to create a subset of the Cartesian product where it can be seen as a function. So that's true. That is absolutely true. Any questions at this point? Yep.
Would that last one work when you put those two first ones into a set?
No, that would not work either. Okay, so I see what you mean. So the question is, okay, so this is going to look a little confusing. The question is that going to work? Well, it violates another rule. Okay, the rule is every element in a function has to be inside the Cartesian product between the domain and the codomain, right? So when you look at this set here, can it be the result of a Cartesian product? Can it be an element of a Cartesian product? Why not? It's not even a tuple. Okay, so that's why by being this guy not being in the Cartesian product between x and y, we can automatically reject this particular f as a function. It cannot possibly be a function. Yep.
But if you change that so that A returns the set 1, 2, then it would still be a function. If you return multiple values, it just has to be the same thing, right?
Say that one more time.
Have A return the set 1, 2 instead of just 1 or 2.
Okay, that wouldn't work either. Let's check that out. So we'll change that to what you said. Okay. So you're basically saying, this is 1, 2 as a set.
So then we would have to change to be sets.
Correct. Yep. So right now it doesn't work. Well, you still have that problem of A. Oh, okay, never mind. That thing is gone. But now we have the problem of the set of 1, 2 is not an element of the codomain. So that means this tuple is not going to be inside the Cartesian product between the domain and the codomain, and that's why this particular f does not work. Yep.
So just to clarify, you don't have to use all the elements in the codomain?
That is correct. Now, whether you use all the elements in the codomain specifies a property of a function, but in order to be a function, there's no restriction of whether you have to use all of them or not. Question? Yep.
Can X be an empty set in order to produce an empty set?
That's a good question. Okay, so we'll now move on to talk about what if X is ABC, Y is an empty set. And we want a function f that maps every element from X to Y. Okay, so I put a big question mark. Oops, nope, I clicked. Okay. Put a question mark here because we want to say, is this even possible, right? Is this possible? Okay. Yep.
Say no. Like you already have an X, so you have to have it has to match the Y feature.
Right.
It's not like the opposite where if you don't have X, it couldn't be true.
Yep. Okay, so let's think about it from several perspectives. Okay, so the first perspective is what is the Cartesian product between these two? In other words, if I just want to figure out what is the Cartesian product of x and y, the domain versus the codomain, what is that going to look like? It's an empty set, right? Okay. So f has to be an empty set now, doesn't it? Because f has to be a subset of the Cartesian product between the domain and the codomain. Okay? F being an empty set, but the domain being non-empty, now we have a problem because, hey, the rule says every element in the domain has to map to one and only one element in the codomain. Nothing is mapped. None of the element of the domain is mapped. So it doesn't work. Okay, it's just impossible to create a function when the codomain is empty, but the domain is not empty. So I'll just write it here. Okay, it is not possible to have a function mapping a non-empty domain to an empty codomain. It's just not possible. Well, if this is not possible, what about the other way around? Has that crossed your mind? What if we flipped it around, right? So x is empty this time, and then y has a bunch of elements. Okay, we'll just say 1 and 2. Okay, we just like that set. Okay, and we say, can we create a function that maps from x to y? Does a function like that exist? Yep. Okay. F has to be an empty set, but that is a proper function. What? How can this be a proper function? Well, the requirement is, yeah, go ahead.
Y equals 2.
Hmm?
Y equals 2.
Y equals 2.
That would be a function that works for that.
No, this doesn't work at all. This function it doesn't map anything. So it cannot return anything either. Yep.
But it is a subset of
It meets all the requirements. Is F a proper, is F a subset, not proper, but a subset of the Cartesian product between x and y? Yes. For every single element in x, in the domain, each one is mapped to one and only one thing in the codomain. Yes. Do you guys still remember the for all function that we talked about earlier? The default answer is yes. So if there's nothing, the requirement is met. So it's not a very useful function, but it is a function. Yep.
So it works because of that, but it doesn't.
Correct. Yep. In a way, that's basically what it means. Yep. Yep. Mm-hmm.
That would be an example of a subset, not a proper subset.
It's a subset. Correct. Yep. But for everything else, it has to be a proper subset. Well, if your codomain has, let me think about it. If your codomain has only one element, then the function is the same as the Cartesian product. Because there's only one way to make it happen. So let me say that once, okay? So if you consider f as a function that maps from the domain x to the codomain y, okay? If the cardinality of y, which means that's how many elements there are in y, let's say there's only one element in y, implies, okay, and bar x bar is greater than or equal to 1. Okay, so x is non-empty, cannot be empty. Because when x is empty, well, that works true, I think. Actually, just that is enough. Implies f equals to the Cartesian product between x and y. Okay, let's think about this a little bit. This just occurred to me, okay? So it is not a proven theorem, but let's think it through and see if it makes sense or not, okay? There's only one element in the codomain. Y is what we call a singleton, okay? It has got one single element in it. X can be anything, okay? Can have an infinite number of elements, can have one single element, can even be empty, okay? So in this case, I claim that whatever function you create, there's only one function you can create, okay? And that function that you create is actually just the Cartesian product between x and y. Does that make sense? It has to be. Right? If x is empty, so is this. And f has to be empty as well. But in this case, because your domain is empty, f, the function being empty, is fine. It is still a function. Yep.
So then wouldn't this be an equality
It is an equality.
instead of equals? No, so
Oh,
y
it goes the other way around?
shouldn't it go both ways then?
No. If I tweak this side, this comparison a little bit, it will go the other way around. Because what if x and y are both empty?
Well, then the cardinality of y is not equal to 1. So you just get a complete.
Let's see. So this is a sufficient condition for this to occur, and you are saying that this becomes, you want this to become if and only if, right?
Never mind, I see what you
Yeah, because if it's if and only if, then the right-hand side implies the left-hand side as well, but it does not. Yep. Okay, so this is cool. Are we ready to switch back to the notes? Yes? Because what is coming to you is a bunch of symbols. And let me see, where is that? Okay, this is what I want to explain here. In order for, so I'm still using the same notation. F is the function, X is the domain, Y is the codomain. Okay? So what is this saying? What is this statement saying? F is a function if and only if this whole thing is true. Okay? But what is that saying? How do you start to read this thing? What do you think? So we'll focus on just this long, ugly expression now. Okay, so we only consider elements of the domain, right? So we consider each and every single element that we can pick out from the domain, and we give it a name of E. Okay, so that takes care of the quantifier. So you can look at the quantifier as a loop, a for loop. We are just basically saying, okay, how do we pick something to be considered? Okay, so now that we know what E is a element of X. What is inside this, the outermost parentheses here?
Such that the cardinality.
Aha, very good. So we are reading from the outside in, right? Because we are looking at the cardinality. The bar starts here, and then the end bar ends here. And what are we doing with the cardinality? The cardinality has to be 1. Well, which is the same thing as saying 1 and only 1. Okay, so what has to be 1 and only 1? The cardinality of this particular set. What set are we talking about? Okay, inside the set, each element is a 2-tuple. P and Q. What P and what Q? I'll tell you about that, such that, right? The first one is just E. So I could have just used E here and not use P, but this is okay as well. So the first thing of the 2-tuple is E itself, which is an element from the domain. Okay? But I have another restriction. PQ as a whole has to be an element of F. I'm picking every element in F that starts with E as the first element in the 2-tuple and put it into its own set. That set, the cardinality of that particular set, must be exactly 1. So this is the long, well, I shouldn't say long, but this is the mathematical way to say exactly the same thing in the previous case, where I said, every element in the domain must map to one and only one thing in the codomain. Except this time, I did not use English. Yep, question?
If we remove the P equals E,
Uh-huh.
replace every occurrence with P with E, we would have the same statement.
Yep. Mm-hmm. All right, so are we okay so far with the symbols, what a function really means? Okay. Is square root a function? The square root of? But there are 2 roots to every non-negative number. So if you look at 4, what are the roots of 4? It's 2 and negative 2.
So I thought the function's square root only produces the opposite. It only produces, it doesn't produce, well, there are 2 answers to what could result in
Right.
4, but square
Mm-hmm.
root only produces 2.
I don't know the nomenclature, of the symbol, this thing here versus the root of a number. So there has to be a separate symbol or another way to represent the root of 4, okay, as opposed to the square root of 4. So if I say the root of 4 versus the square root of 4, this one is implicitly non-negative, but the two roots of 4 are 2 and negative 2. So I'm not really sure about the nomenclature or the symbols of how that is represented. Yep. X squared equal to 4.
Yeah, x can be negative.
That describes the root. Yep.
Where can I know square root is give you both a positive and negative value. Just like when you use quadratic formulas, you get a positive and a minus.
You're solving for x.
Right, but the symbol only returns the non-negative version. Yep. And that's why you need to specify plus minus, because it is implicitly just the positive. Okay, so we are good. Now we are looking at an example. So why are we even talking about this? And why do we need to look at functions in this kind of funky way? Why don't we stick with functions that we know of that are nice and easy, like f of x is 2x? Why do we consider these arbitrary mapping? So let's think about this problem. So we'll look at this problem of how do we express a sorting algorithm. How would you describe it? So let's flip the roles, okay? You're the professor, I'm the student. And you basically want to make an assignment of, okay, this homework assignment is, okay, let's not even sort, okay? Let's just specify a program that can confirm whether an array is sorted or not, okay? So the input of the function or the input to the program is an array, and the output of the program is really just to say, yes, it is sorted, or no, it is not sorted. And you can choose increasing order or decreasing order. That part is not important, okay? So how are you going to write the description of that assignment? Assuming the concept of sortedness, the concept of being sorted is vague, and you need to describe it in a very precise way. Yep.
The value has to either equal or be greater than the value before it.
Okay, that's one way. Yep.
Imagine we had a predicate with two elements, A and B, and said, is this the proper order?
Mm-hmm.
Sorted list would then be wherever the two elements in that set, every two consecutive elements would
Okay.
satisfy that predicate.
Okay, so I can cheat now. Okay, so based on what you guys just said, I can now cheat. So let's go ahead and go to here. Okay, so let's say we are given array A. Okay, so A is the name of the array. Return a Boolean. Okay, to indicate whether A is sorted, and I'll be more specific here, in a non-decreasing order. Okay. So let's say that's the homework assignment, and I'm going to do the following. Okay. So we'll also need one more thing, with a length of n. Okay. Because in C and C++, if you just pass an array into a subroutine, the subroutine has no idea how long the array is, right? Which is a big problem. Okay, so I'm going to write this loop here. I'm going to say for I equals to 0, I is less than n, plus I, very typical loop to go through all the indexes that are valid in this particular array. And I'm going to do this. I'm not even comparing. Oh, and then I say return true. Well, you didn't say that I cannot change the array. So I changed the array. Every single element has exactly the same value. So now the array is sorted in a non-decreasing order. Then I return true. If you describe as what you said, you have to give me full credit. Yes? Yes. Okay, so given that is a key issue to describe, how to detect whether an array is sorted, right? So now, how do you describe an algorithm that actually sorts the array? Okay, so can we? How do we now describe an array, an algorithm, the output of an algorithm that sorts an array? It's all here. I don't want you guys to spend too much time to read it. I want you to kind of think about it on your feet a little bit. Okay, so how do I describe the outcome of a sorting algorithm in a concise and precise way so there's no ambiguity? The student cannot come back and argue and go like, but you didn't specify blah blah blah. This program does what what you said that it should do, and I should get all the full credit. Okay, so there are two things, right, in sorting. You cannot, now, in the case of a non-increasing order or non-decreasing order, the incoming array can have duplicate items, right? So let's say it has 5 ones and 5 twos, but they're interleaved in a particular way, so the array is not sorted, okay? If I just, replicate all of those, the same value throughout the array, that's not good. Okay, because if I just say, oh, the original array has 5 ones and 5 twos, I'll just make 10 ones, in the resulting array. That's not sorting. Agreed? All right. What about this? 6 ones and 4 twos. Would that be okay? No. 1 1 and 9 twos. Not okay. So now how do you describe the relationship between the resulting array and the original array? How do you describe it? Mathematically, using conditions, not verbally, and say, how do you describe it? Yes. Go ahead.
Yeah, for all I.
Uh-huh.
Starting from 0 and then from an array.
Yep.
So A also A brackets I
Mm-hmm.
must be smaller or equals to A bracket I plus 1.
Okay, so that specifies the relationship of adjacent elements. Yep. Mm-hmm. And then the crucial piece is to relate and say that everything from the beginning has to be somewhere in the end. That piece is the difficult piece. Okay? So, so if you read this part, I use a function to do that. So k is a series of numbers representing the values of the original array. So k0 is the value of the first element. K1 is the value of the second element, and so on. The array itself is A, okay, and you're doing in-place sort, which means the values of A is going to change between the initial phase and the final phase of the entire algorithm. So in this case, okay, let's read this notation, see if we understand what it means. Okay, for all I such that I is an element of this range of integers, from 0 all the way up to the size or the length of the array minus 1. In other words, all I'm doing here is to say I is a valid index into the array. That's all I'm saying. Okay, for each valid index into the array, the following has to be true. Okay, what is the following? The following says A bracket I. Okay, whatever I you pick is fine. A of I has to equal to k, and then in subscript, f of I. In other words, I have some kind of weird function that will map this I to potentially something else. Okay? So in addition to this, in order for this to be an algorithm that is sorting, the function has to have one particular property. Okay? It has to be what we call a bijective function, which means each element in the domain has to map to a unique element in the codomain. Okay? Now, I know this is a lot to take in. But this is why it is important to talk about functions in a very, very general sense. This is not quote unquote mathematical in a sense where there's a particular mathematical meaning of the output of a function. The output of a function can be just for the sake of mapping something so that we can express a certain thing that we want to express. Is that okay? All right? Yep.
Can we compare sets and tuples?
Huh?
Can we compare sets and tuples?
Yes.
Given
You can
that
compare, but you can only get equality. You cannot have greater than or less than.
if we took the notion of array and turned it into a tuple, it would have the same properties, right?
If we take the concept of
An array.
an array, turn it into a tuple, yes.
Could we say that in order to get the constraint, all elements in it would have to be in the output, that would have to be one has to be a subset of the other. I'm basically trying to equate the two.
Yep. Okay, the problem with equating is what if you have duplicate elements? Because when you have duplicate elements, you have to have the right count of the duplicate elements. You cannot have the wrong count and just say that, oh, 1 and 2 are both in the incoming array and now they're both in the outgoing array. That alone is not enough. If you start with 5 1 and 5 2s, you have to end up with 5 1s and 5 2s. So that becomes the difficult part. So that's why we need a function that we call a bijective function. And basically it says it is a mapping, okay, of the incoming values that we call k to the outgoing values which we call a of I, okay? And it has to be a unique map. Okay? This thing that starts here ends up here. Nobody can end up there except for this guy. Okay? This thing here that we start with ends up here. Same thing. Okay? Yep.
So in terms of that question about where we allocate the functions, would it just be adding an additional criteria for value?
Yep. Yep, you're correct about that. So this part only talks about the part of making sure that everything in the incoming array is in the outgoing array. And then on top of that, we also have this to make sure that the outgoing array is quote-unquote sorted. So this part only basically says an element in the outgoing array has to be less than or equal to the next thing in the array. So these two combined would describe what the assignment, or the correct outcome of a program, for that particular assignment. So they should have put this class as the first class in the entire CISP series, because otherwise there's no way to describe homework assignments, even in CISP 300. Hmm?
Some system this class is called nice first
Yep.
first year semester.
Yep. So that brings up a few important points. Okay, that brings up a few important points. I'm glad you pointed that out. Is computer science math? It's a specialization of math. So you're right. So computer science is a branch of mathematics. We can pretend it is not. Doesn't change the fact that it is. So if you want to read more about that part, you can look into. We'll see this guy's name, okay? So we'll examine Dijkstra's algorithm close to the end of this semester, but you can look up his name and just look up computer science is math, okay? So you will find his quotes, okay, of how he viewed computer science. Basically, he says, computer science is a branch of mathematics. But I can program without knowing all the higher math stuff. Yes, up to a certain point. Okay, so the analogy of that is basically saying, how many people think that I can play basketball? Well, it depends on what you call playing basketball, right? Okay, I can run around in the court. I can dribble a little bit, maybe for 3 minutes. and I can shoot the basketball. Okay, maybe one time out of 20 it will make it. Okay. Yes. So from that definition, yes, I can play basketball. But can I play basketball to make a living? The answer is no. Okay? Same thing applies to programming. Okay? Can this person program? Yes. Can this program make a living out of programming? That becomes a slightly different question. Can this person make a living out of programming and keep progressing in his or her career, to a higher point and a higher point and a higher point? That becomes yet another question. So math, being computer science being a branch of math, is kind of it relates to that, because it's basically saying a good foundation of mathematics will take you further. Okay, technically speaking, it will take you further when you are in a computer science career. Is that okay? It doesn't mean that if you don't like math, you cannot be a developer. That is not what I'm saying at all. It has to do with how effective you can be as a developer. So something for you guys to look up, it's kind of interesting. How many people so it brings up another point that I think is kind of important for you guys to think about. How many of you really enjoyed debugging in cisp 360, 400, and 430? When your program doesn't work, you go like, woohoo, it doesn't work. Now, I'm a professor, right? And I have taught cisp 310 assembly programming for years, okay? And every time someone says, my program is not working, I go like, oh, okay. I want to take a look. Because, to me, understanding why something is quote unquote not working is actually not entertaining, but it's very rewarding to find out why something is not working. Okay? It can be the tool, it can be the program itself, it can be a lot of things. So that is also the mentality that you might need to keep in mind if you want to pursue a career in development. Okay? Software development is mostly debugging. If you think about how much time you spend on writing new code and how much time you spend debugging existing code, what is the ratio? 20-80? So 20% writing new code, 80% debugging. That's about right. That sounds about right to me. So what differentiates a good programmer, a good developer, from a quote-unquote bad developer? It's that ratio. Okay? Your programming style can help determine that. Whether you use object-oriented programming correctly can determine that. Whether you reduce the use or eliminate the use of global variables can determine that. How long your function is can determine that. So that is the concept, okay? It's not about, good programmers do not have bugs. No, absolutely not true, okay? It is how contained the bugs are, how quickly you can locate the bugs because of the structure of the program, and how you can apply logic to quickly locate and go like, oh, the program is bombing over here, and you can run the program backwards to find the point where the program is going onto the wrong path. So that is basically, that differentiates, someone who's effective as a programmer, as a developer, from someone who is not effective as a developer. But that has to do with math. All of that has to do with math. All right, so I think we are close to the end of this module, but not at the end of this class. The next module talks about the 3 properties that we can use to describe a function. So we got injection, surjection, and bijection. And more of these symbols here. If I know that f is a function already that maps from the domain x to the codomain y, we say that f is injective or f is an injection if and only if this is true. Or it is the same thing as to saying this, okay? What is that saying? Okay, first of all, does this look slightly familiar to you? Just the format, not exactly the detail, but the format. Looks a little familiar, okay? But there are important differences. The first difference is Q is an element of Y. We are only concerned about elements. For each element in the codomain, can we say this is true? All right? So that's important. So now we look into this part here. We are only locking down the Q using the quantifier. So P is quote unquote free floating. Okay? So we are now counting the number of things that map to Q from X. And we can have up to one thing mapping to everything in the codomain. Okay? This whole thing, the cardinality of this set is less than or equal to 1, means up to 1, right? It can have up to one element. So that means if you look at everything, each element in the codomain, it can only be mapped to from up to one element in the domain. If this requirement is satisfied, the function is called injective, or you can call the function itself an injection. Are we doing okay so far? How about some examples? So we'll focus on this, okay? Move it up here, and then we'll look at some examples. So I would look at X as ABC again, Y as 1, 2. Okay, so if X is my domain and Y is my codomain, can I make a function that is injective, given this definition of injection? It is not possible. So every time you have more elements in the domain than there are elements in the codomain, that function, you cannot have a function that is injective. In other words, you have to reuse at least one element in the codomain. Is that making any sense? If X is my domain, Y is my codomain, and I want to make a function out of it, don't you think, at least one element of Y needs to be mapped to more than once? Well, that function cannot be injective. So the first requirement for something to be an injection is the cardinality of the codomain cannot be smaller than the cardinality of the domain. Okay, fine. So now we just say, how about making it bigger? Okay, 3 and 4. So now it's bigger. And f is a function going from the domain X to the codomain Y. And I say, okay, what about this mapping? Does it work? A1, B2, and C3. As simple as it gets. Is that injective? Well, first of all, is it a function? Because if it's not a function, we don't even need to label it injective or not. Is it a function? For every element in the domain, it is mapped to one and only one thing in the codomain. Yep, okay, it is a function. Is it injective? In other words, if we look at everything in the codomain, it's only mapped to from the domain up to once. Can be 0. Yep, that works too. 1 is mapped to only once. 2 is mapped to only once. 3 is only mapped to only once. 4 is mapped to 0 times. But that's okay, because according to, I got it covered. So according to the requirement, it only has to be saying up to 1. 0 is fine. You can have elements in the codomain not mapped at all. That's perfectly okay. You just cannot have more than one thing mapped to the same thing in the codomain. So that's called injection. What do you think surjection is going to look like? Look at this. Okay, let me try to get both of those statements on the screen at the same time. Well, this is as close as I can get, but people from the back may not be able to see it. There you go. This is injection. This is surjection. What is the difference? Okay, let's do a very careful comparison. For all q in y, okay, they both start with for all q in y, no problem. You look at the set, the description of the set, they're the same. Okay, all elements in this set are two tuples, where the first thing is coming from somewhere, we don't know where, but the second thing is the q that we have already picked out. Okay, and it has to be an element of f. Okay, that's true as well. So the only difference is that one is the first one in injection is less than or equal to 1, which means up to 1, can be 0. And then in the second case, it's greater than or equal to 1, which means it can be 1, but it can also be 2, 3, 4, whatever. Is that okay? So the second one, or surjection, the easy way to say that is simply saying everything in the codomain is mapped to. Okay? Any number of times. It can be 1, can be 2, but it has to be mapped to, so at least once. Is that okay? All right, so if that is the case, let's see if we can make some examples out of surjection. Okay. Well, actually, we can just start with this one. Okay, so we'll say this one is injective. There we go. So can we make it surjective based on x having 3 elements and y having 4 elements? No, it cannot be surjective because because there are fewer things in the domain than there are things in the codomain, and the mapping is mapping one thing in the domain to one and only one thing in the codomain. So it's not possible for this setup to be surjective. Okay. So we'll use another example. So we'll say x is just ABC, y is 1, 2, 3. Looks pretty good. F is a function mapping x as a domain to y as a codomain. Okay, so let's try this one. A1, B1, C1. First of all, is it a function? It is a function. Everything in the domain is mapped to one and only one thing in the codomain. It's a function. Is it injective? It's not injective. It's not injective because exactly, because more than one thing is mapped to at least one element in the codomain. In fact, it's 3, right? All of A, B, and C are all mapped to the same thing in the codomain. Is it surjective? This particular mapping, is it surjective? What is surjective again? Everything in the codomain has to be mapped to at least once. Okay? 1 is mapped to 3 times, satisfies that requirement. What about 2? Not mapped to? 0. Oh, wait, 0 is not greater than or equal to 1. Problem. Okay. So even though this is a function, it is neither injective nor surjective. Okay, let's try another example. A1, B1, and B2. Okay, forgot about that. And B3. Okay, what about this one? I don't even want to say anything about injectiveness or surjectiveness because it's not even a function. Why is this not a function? What is the requirement of a function again? Every element in the domain has to map to one and only one element in the codomain. C is mapped to 0 thing in the codomain. Does 0 meet the requirement of 1 and only 1? Nope. Okay, well, that's an easy one. So we say it's not even a function. Okay. So the last one is easy. Okay, because I have to throw you this bone. and say that, yep, this one is good. Okay, so first of all, is it injective? In other words, is every element in the codomain mapped to up to one time? Yep. Okay, 1 is mapped to once. 2 is mapped to once. And the last one is all 3 is also mapped to once. Very good. So we'll write down it's injective. Okay. Is it surjective? It is also surjective. Why is it surjective? What is the requirement to be surjective? All the elements in the codomain must be mapped to at least once. Okay, once is fine, okay, but 2 is fine too. So 1 is mapped to, good. 2 is mapped to, good. 3 is mapped to, good. Okay, so it is both injective and surjective. And guess what name we can call it now? It is also bijective. I don't know. Do you guys prefer hands or thus? Okay, or therefore. Okay, so any function that is both injective and surjective is by definition bijective. Or you can say bijective if and only if injective and surjective. And bijective is really cool, okay? Because when you have a bijective function, it guarantees to have an inverse. In other words, you can give it a value, it maps to something. But if you say, oh, it mapped to this, but what mapped to it? You can find that answer as well. So bijective function is always reversible. And that makes it really, really helpful in many types of applications. So we'll get to that next Monday. Okay? So your job is to read all the modules at least up to this point, and if possible, just read ahead of me. Okay? I know this is heavy-duty reading, so you might want to kind of have your notes on the side so that you can annotate the symbols, and then you can just write down your understanding in your words, okay, next to the equations and formulas and whatnot. Okay? All right. So I'll see most of you on Monday, and please study because I hate these long breaks of time.